we are going to start off a new physical quantity, which is electrostatic potential energy. Okay.
Yes, sir.
So till now we have done force, we have done field. The variations of the fields, that means fields due to multiple point charges placed at different positions. That means using I cap and J cap, practice of that. Number 2, electric field due to uniform charge distributions along length, area, volume.
Yes, sir.
And number 3, a little bit of non-uniform charge distribution, how we usually do it, and we practiced it for linear. In future, when we get time, we will definitely go for aerial and volume also. Even we will use cylinder.
Yes, sir.
So enough of force and field. Now we have two more physical quantities. One is electrostatic potential, other is electrostatic potential energy. And these two are more or less related. But first, let us go to electrostatic potential energy. Okay?
Yes, sir.
So you asked me, what is potential energy itself?
Yes, sir.
Right? So what is potential energy in general? You have heard of gravitational potential energy, and the same gravitational potential energy in the work energy chapter you have seen as mgh also,
Yes, sir.
and in gravitation chapter you saw it as minus gm1 m2 by r. See, in general, what is potential energy? What is kinetic energy? Kinetic energy is the energy that is associated with the motion of a particle.
Yes,
That
sir.
is clear to everyone, half mv square. But what is this so-called potential energy? Potential energy of a system, I am not giving the description of textbooks and all, I am just giving you the meaning of it. Potential energy of a system should be the energy which represents the potential of that particular system. If that fellow has named it potential energy, then that should be the energy which should have something to do with the potential of that system.
Yes, sir.
But what actually describes the potential of anything? What do we mean by potential of the Rock, WWE?
The capacity.
Correct? The ability,
Yes, sir.
the capacity, right? I think ability probably becomes more kind of a potential. Capacity can also be used as how much water is there in your water bottle. Volume also can be, but volume does not really describe the potential. Maybe not.
Yes, sir.
But eventually, when we come to that, when we talk of rock and when we talk of potential, so he is in wrestling. So obviously, we will talk of how strong the man is, right? The person is.
Yes, sir.
But let me take some other example. What is the potential energy associated of a Pomeranian? A Pomeranian, depending on the capacity, like you said, of the energy that it has and the way it is made by the God, it will bark
Yes,
that
sir.
way only
Yes, sir.
compared to an Alsatian. If an Alsatian will bark, we can hear it from very far, right? And the
Yes,
thing
sir.
is, Alsatian barking actually can create a little bit of fear. When Pomeranian barks, I am like laughing at it.
Yes, sir.
I had a friend who had Pomeranian, and that Pomeranian is literally ferocious. I mean, it will just attack you only till 1 millimeter distance of you. So it will come running from some 100 meters, 20 meters, whatever, will come like a lion till 1 millimeter and then bark. I'm like, bite it. Let us see. So that is Pomeranian. Potential energy of a Pomeranian is this.
Yes, sir.
I never do this comedy with Alsatian. I used to play with Alsatian in my childhood. Throw ball and then snatch ball from its mouth and all those things. But I would never give this kind of a comedy to Alsatian because it will bite. And if it will bite, it will not leave it. So, what exactly is potential? It is the ability, it is the capacity of that particular thing to do something.
Yes, sir.
So, in terms of dogs, we can say the strength with which it can bite eventually comes to force. In terms of Rock, WWE, the strength with which he can wrestle comes to force.
Yes, sir.
The potential of a student to solve 200 problems a day again comes with the mental strength that that particular person has.
Yes, sir.
So I thank you. But actually, if you look at it, the word potential is somewhere related to some kind of strength. It can be mental strength or physical strength.
Yes, sir.
Gravitational force, physical strength. Electrostatic force, physical strength. But we can use that particular potential word for mental strength also.
Yes, sir.
Are you getting my point?
Yes, sir.
So, first thing that I want you to remember forever and never forget is that potential energy has something to do with force. Do you agree?
Yes, sir.
If you have any doubt, clarify right away. Any kind of potential energy, electrostatic, magnetic, gravitational, or if possible, any other. Nuclear forces will also have potential energy. In atomic structure chapter in first year, you must have seen U is
Yes,
equal
sir.
to a negative function. That
Yes,
U
sir.
is also called a potential energy. The potential energy word can be associated to any system which has a force in the first place. When the force is gravitational force, you will have gravitational potential energy. When the force has electrostatic in it,
Then everything should have potential. Because
everything that has something to do with force will have potential.
yes, sir.
So, the type of sleep that I undergo has nothing to do with the force abilities that I have, physical or mental.
Yes, sir.
So, that is something related to peace, has nothing to do with strength, physical or mental strength, nothing to do with strength. How peaceful I am doesn't show how strong I am mentally.
Yes, sir.
Are you getting my point? So not everything has to have some association with force is what I am saying. If you talk of mechanics or if you talk of physics that we have, like I am saying, electrostatics, magnetic, gravitation, or nuclear forces, and blah blah blah. If you look at this particular syllabus, all of them are having force, right?
Yes, sir.
So as you said, everything has potential in it. But if you look at, like I always say, just look at it from a layman perspective. Look at it at 360-degree viewpoint. Not everything has to have a potential. The word potential need not necessarily go to everything. The quality of food that I am eating has nothing to do with potential of it. Quality. The quantity of the food that I can eat is dependent on the stomach
Potential you have.
capacity.
Yes, sir.
Potential, how much I can eat. But the quality of it has nothing to do with it.
Yes, sir.
So, why 2 moles of hydrogen mixed with oxygen to form a molecule has nothing to do with potential energy. It has something to do with valency.
Yes, sir.
There is no potential story in that. The hydrogen oxygen bond energy in a hydrogen H2O molecule has something to do with potential, because the atoms are having forces between. The bond
Yes, sir.
energy of hydrogen and oxygen in an H2O molecule has something to do with potential energy.
But individually also they will have some potential energy.
Individually also will have some potential energy because there are nucleons and there are electrons. All of these have forces of interaction. Therefore, independently also they will have some kind of a potential energy.
Yes, sir.
So first thing, I hope why the potential energy story comes into play is clear, right?
Yes, sir. But why only force?
Why only force?
Yes, sir.
Why, which other physical quantity do you want to get in this story? Speed, motion may be related to force, might not be related to force. In vacuum, a satellite is moving. It will move with a constant velocity.
Yes, sir.
With respect to a given frame of reference, it will have a particular velocity. Therefore, it has kinetic energy.
Yes, sir.
There is no force of interaction of it with anyone. Therefore, I will not assign anything called potential. So, which other physical quantity do you think will have a role in potential energy? Your friend snatched your pen. So,
Yes,
the
sir.
amount of force that you will apply to get it back defines the potential abilities that you have. Everywhere, everywhere, you just look at it in a 360-degree viewpoint. Whenever you can use the word potential, some kind of a force or some kind of a strength is associated to it. Physics or not
Yes, sir.
physics is you're free to look at it in a 360-degree view. Wherever there is force, there is potential.
Yes, sir.
And wherever there is potential energy.
Yes, sir.
Okay?
Yes, sir.
Now let us understand one electrostatic derivation. Usually any derivation in work power energy, we give different kind of examples to discuss. Here we discuss in a different way. Either which way, you will get more clarity about potential energy right away.
Yes, sir.
Now, suppose I have a fixed charge, let's say capital Q.
Yes, sir.
Okay. By saying that this is a fixed charge, that means I am not allowing this charge capital Q to move. And let us say it is a positive charge. Okay.
Yes, sir.
Now, at an infinite distance, at infinity, I have another charge, positive charge, let us say small q. But the small q is like our test charge. We can do whatever we want. So basically, I am going to move it in this particular situation. Okay.
Yes, sir.
Now, when both the charges are at infinite distance, according to our electrostatic force, what is the force of interaction between them?
It there won't be any force of
Zero.
interaction. Yes, sir.
Zero.
Yes.
When there is no force of interaction, when there is no force, there is no story of
Okay.
potential energy.
It doesn't have any skills to attract it closer.
But let us say from infinity, I started to slowly, very slowly. Okay. Why am I saying very slowly? I want its kinetic energy to be negligible.
Hmm.
Very slowly, but with constant speed, I will come. Very
Yes, sir.
slowly already is a negligible velocity or negligible speed, and also I will come with constant speed. Why? I will explain it later. First, let us look at the potential story. The reason why I am keeping this very slowly story is basically to keep the change in kinetic energy to be zero. Are you getting my point?
Yes, sir.
The only reason we are specifying that I am keeping this, I have to say that I am bringing it with a particular speed because that describes motion, right? Otherwise, the charge q will be there only.
Yes, sir.
There is no statement I can make by saying I am bringing this charge towards the bigger charge or whatever, capital Q, with a zero speed. Okay.
Yes, sir.
Zero speed or zero velocity means it is not moving only. So therefore I choose for my own convenience. Very slowly I am going to bring this plus q small q charge closer to capital Q charge. Correct?
Yes, sir.
Okay. Now let
Yes.
us say I brought it to a particular point. Let's say this point is A. I brought it to a particular point B.
Yes, sir.
I brought plus q to a particular point B. Both are positive charges, therefore, can I say that there will be an electrostatic force of repulsion right now?
Yes, sir.
Okay, there is an electrostatic force of repulsion. Correct?
Yes, sir.
And what am I doing? I am bringing it very slowly, and that too, I am bringing it with a constant velocity, or you can say constant speed, whichever you feel like. Okay.
Yes, sir.
Why am I bringing it with a constant speed very slowly so that the change in kinetic energy remains zero
Yes, sir.
in my story? Okay.
Yes, sir.
First of all, while bringing the plus q charge closer to the capital Q charge, I am already coming across a force of repulsion.
Yes, sir.
That means I have to apply a force in the direction of motion to shift it from infinity to point B.
Yes, sir.
Is this clear?
Yes, sir.
I have to apply a force, right? Let us say the force applied is Fa, and the direction of Fa will be basically towards the other charge, correct?
Yes, sir.
First point, clear?
Yes, sir.
So, to maintain constant velocity, can I say that the force that is applied should be equal to the electrostatic force at every given point? Hello everyone, welcome to Veracious Academy. My name is Anil Kumar. I am an alumni of IIT Bombay. I have done my BTech from Mechanical Engineering. I have been teaching physics for the past decade for JEE Mains, JEE Advanced, Neet UG, and other competitive exams. If you're interested to attend my sessions, please find the contact details in the description below. Let's get started with this lecture. Enjoy the video. Suppose I am pushing you with 10 Newton from this direction, and your brother is pushing you with 20 Newtons in the opposite direction. 20 and 10 are not same, so you will have a net force of 10 Newton.
Yes, sir.
And according to Newton's second law, net external force is rate of change of linear momentum.
Yes, sir.
When your linear momentum is changing, and if mass is not changing, definitely velocity is changing.
Yes, sir.
When velocity is changing, I cannot say constant velocity.
Yes, sir.
For a constant velocity situation, I have to say the net force acting on the particle at every instant of its journey should be 0.
Yes, sir.
I'll go slow. To say that I am moving it with constant velocity, and I am saying that there is a force that I have to apply externally against the electrostatic force. But to maintain this constant velocity, I have to make sure that the net force always is 0.
Sir, could you tell it again?
I want the net force to be 0. Why do I want the net force to be 0? So that the rate of change of linear momentum of that particular system is 0. Why do I want the rate of change of linear momentum to be 0? So that I can say that I am maintaining a constant velocity.
Yes, sir.
This is a concept of mechanics.
Yes, sir.
Okay. So I'll repeat again. No hurry. Understanding is very important. Thereby we get a clarity of what this potential energy story is in general.
Yes, sir.
If I maintain net force as 0 for any system, that means I am maintaining the rate of change of linear momentum to be 0.
Yes, sir.
If the rate of change of linear momentum is 0, that means my initial momentum and final momentum are the same.
Yes, sir.
If my initial momentum, final momentum are the same, and mass is also constant, velocity is constant.
Yes, sir.
Are you getting my point?
Yes, sir.
This is Newton's second law. Net force
Yes.
is rate of change of linear momentum. If that is 0, that means this is 0. If this is 0, that means P1 is equal to P2, or initial momentum is equal to final momentum.
Yes, sir.
If initial momentum, final momentum are same, and if mass is also same, then velocity is same.
Yes, sir.
If velocity is same, that means it is constant velocity.
Yes, sir.
Or to maintain constant velocity situation, the condition is I should maintain the net force on the system at any situation to be 0.
Yes, sir.
So suppose I maintain net force to be 0 initially when you are watching. Suddenly pen fall down. You went to pick up the pen. I applied some net force. And then again I said no, net force 0. That is cheating.
Yes, sir.
Because if I will maintain a net force anywhere, there will be a change in momentum, there will be a change in velocity. So while initially when you are looking, you are seeing it going with 1 kilometer per hour, and then you picked up your pen and you saw 10 kilometer per hour. What is this? Change in velocity.
Yes,
For any kind of a situation, to maintain constant velocity, I have to have the condition that the net force should be 0.
yes, sir.
Along with this, I am attaching a tail that net force should be 0 everywhere throughout the journey, because the net force to maintain 0 I have to maintain the applied force should be equal to the electrostatic force.
Why is electrostatic force coming into play? Because you took a test charge.
Because we took a test charge, and when it comes to a distance r, we know that there will be going to be electrostatic force repulsion. At infinity, we have zero force.
Yes, sir.
Suppose at this point,
Okay, sir, I got it.
right?
Yes, sir.
So I should go slow. So this is clear to you.
Yes, sir.
In any system, in any situation, to maintain constant velocity, the condition that should be maintained is net force should be zero.
Yes, sir.
In this particular situation, when the charge is at point B, I have two forces, applied force towards the charge and electrostatic force away from the charge.
Yes, sir.
Let us now come to story discussion about this. Why should I have an applied this FA is what? Applied force. Applied
Yes,
by
sir.
an external agent. Why should there be some applied force in the first place? Because there is an electrostatic force. Why is there an electrostatic force? Kill Coulomb.
The charges.
Right?
Yes, sir.
Then why should I have an applied force? To maintain net force is zero, whatever electrostatic force is there by nature, I have to cancel it using some applied force, external force.
Yes,
Is this
sir.
clear?
Yes, sir.
The reason FA is coming into play is to maintain this condition.
Yes, sir.
Is basically to cancel the electrostatic force.
Because you first initially thought you have to move the charges with constant velocity.
Deleted statement. Yeah. Let me come back to my statements and follow it. So I'll repeat the story. The reason why I am applying an external force FA is to cancel FE, and FE is there naturally.
Yes,
By
sir.
nature, there is an electrostatic force, and it is a force of repulsion.
Yes, sir.
I have to externally provide FA because to maintain F net zero, because I have to maintain constant velocity, because I don't want any change in kinetic energy, because I only want to discuss about potential energy.
Yes, sir.
So to maintain change in kinetic energy zero, I am maintaining constant velocity. To maintain constant velocity, the net force should be zero.
Yes, sir.
To maintain net force zero, whatever force is present, I have to cancel it using some external force.
Yes, sir.
In this particular situation, the electrostatic force is a repulsive force away from it. So obviously the applied force should be towards the charge, correct?
Yes, sir.
I am bringing the charge from infinity to some particular distance r. That means the direction of motion is in this direction, correct?
Yes, sir.
So the direction of motion is in this direction, correct?
Yes, sir.
Another thing that I used a tail previously is that to maintain constant velocity, I should maintain the net force is equal to zero, and to maintain that, my applied force should always be equal to electrostatic force, and the tail I used is everywhere through the journey. Why did I mean? Because during the journey, the electrostatic force magnitude itself is varying.
Yes, sir.
At infinity, it is zero. And as we are coming closer and closer and closer, the magnitude of electrostatic force is increasing.
Yes, sir.
Is this
Yes, sir. Sure, so you have to keep on increasing.
keep on? So your FA is also a variable just to match FE.
Yes, sir.
Are you getting my point?
Yes, sir.
FA is also a variable to match FE, to match this condition, to attain this situation. There, basically, because my desire is to keep the change in kinetic energy zero.
Yes, sir.
Because I want to focus on potential. Is this clear?
Yes.
So that means basically I am applying an external force against an existing force, and I am bringing that particular charge with a constant velocity. These concepts are all clear.
Yes, sir.
Now I am bringing it from infinity to particular situation. Let us say the position vector. I am turning down now to vectors. Okay. The position vector of the charge small q with respect to capital Q at this particular instant is r bar.
Yes, sir.
Then, for a small change in time or whatever, let me displace this particular charge small q by a displacement vector dr bar.
Yes, sir.
But if that direction is taken as positive, I should take this direction as negative.
Minus dr.
Correct?
Yes, sir.
Fine. So my displacement vector is minus dr bar.
Mm.
My FA vector is also in the same direction. This. Correct?
Yes, sir.
By definition, we have something called work done, and work done is nothing but our force dot displacement. This everybody knows, right, from school, in fact.
Yes,
Mostly.
sir.
Work done is force into displacement, right? And it's a dot product.
Yes, sir.
In this case, I want to study the work done by the applied force. Okay. I want to study the work done by the applied force. Because can I say that applied force is the main reason why that fellow is coming with a constant velocity? Do you agree?
Yes, sir.
Applied force is the reason why the particle is moving with constant velocity. Otherwise, this entire story will collapse.
Yes, sir.
I want to focus on the work done by the applied force.
Mm.
Okay.
Yes, sir.
So I can write this as FA bar.
Because electrostatic force is by nature, and here we have to consider applied force.
See, we can discuss in many forms. First, we have to, here there is a further clarity that we need to get. Let me just explain this. The particle is moving from infinity to r bar. That means from right to left
Yes, sir.
under the effect of two forces.
Yes, sir.
Wherever there is a force, there is potential energy.
Yes, sir.
Wherever there is potential energy, wherever there is force, there is potential energy. We have two forces, we have two potential energies.
Yes, sir.
But let me first explain it in a very normal, basic example. So, when I am applying this force FA externally, I am working against the system, right?
Yes, sir.
Suppose I am holding this charge and taking it. So
Mm-hmm.
by nature, if I leave it, it will run away back to infinity.
Mm.
But I am holding it and bringing it.
Yes, sir.
Am I doing any effort?
Yes, sir.
Am I doing any work on the system?
Yes, sir.
Suppose to bring this fellow from infinity to R bar, let us say I have done 50 joules of energy.
Yes, sir.
That much work I have done. Okay?
Yes, sir.
This 50 joules of energy has to go somewhere. Energy is conserved.
Yes, sir.
Where will it go? It will go in the system.
Mm.
Suppose I have this marker over here.
Yes, sir.
And now, using my left hand, I am working against the system. But whatever, how does it matter? I am working.
Yes, sir.
So the work that I have done to lift this fellow from here to above, let us say it is 10 joules. Now, where is
Yes,
this
sir.
10 joules energy right now present?
It's stored in the system.
Who is system?
The marker.
And earth.
Yes, sir.
Okay. So
Yes,
if I
sir.
leave it right now, with the 10 joules only, it is going to fall back from here to here.
Yes, sir.
Are you getting my point?
Yes, sir.
So suppose I am bringing this charge, holding this charge and bringing it from infinity to a position vector r bar. And for example, let us say I am using 50 joules of energy to do that particular thing. Where is this 50 joules stored? The system. Who is the system? These charges are the system.
Yes, sir.
How do I prove that the 50 joules is stored in this system? Leave it, it will run away. With which energy is it running away? The 50 joules that you have given it, with that energy only it is running away.
Yes, sir.
Are you getting my point?
Yes, sir.
I have 5 chocolates. I give you 5 chocolates. You ate 5 chocolates. The energy, which is 5 chocolates, given to you is the energy that is stored in you.
Yes, sir.
Simple.
Yes, sir.
Are you getting my point?
Yes, sir.
Applied force is doing work on the system. Why am I having to do work on the system? Because automatically system will not do.
Yes, sir.
If I do negative charge, then it will do.
Mm.
But if I give positive charge, it will not do.
Yes,
Why
sir.
are you choosing positive charge then take negative charge? No, I want you to understand it better. So I took positive charge.
Yes, sir.
So that I can tell you that I am doing 50 joules of work.
Yes, sir.
And that 50 joules is stored in the system. Who is the system? Plus Q and plus small q.
Yes, sir.
How do you prove? Leave it. With that 50 joules, he will run away.
Yes, sir.
Is this?
Yes, sir.
But I want to find the work done by me.
Yes, sir.
How will I do? The force that I am applying, vector dot product with the displacement that is occurring.
Yes, sir.
Now the force vector and minus dr, these both are parallel.
Yes, sir.
Fa bar is parallel to dA bar.
The force will be negative 1. I'm sorry. The work done will be negative 1.
Fa bar is parallel to minus dr bar. When these
Yes.
two are parallel to each other, that means the angle between them is 0.
Yes, sir.
That means cos of it should be 1.
Yes, sir.
That means the dot product of these two should be A into B into cos 0, which is 1.
Yes, sir.
So I can simply write it in terms of magnitude as this into this.
Yes, sir.
Or let me write it I know you understood, no problem. But let me just write it for the YouTuber's sake. I mean it literally, because these concepts are the concepts that mostly people face difficulty. And now what should I write here? I should write cos 0, right? Because the force Fa bar and minus dr bar, these two are parallel.
Yes, sir.
So basically, only magnitudes, if I have to write, I will write it like this.
Yes, sir.
The electrostatic force magnitude is nothing but the applied force magnitude is nothing but equal to the electrostatic magnitude. Therefore, I will write this.
Yes, sir.
And obviously, it's a variable, so I'll have to integrate
Yes, sir.
from infinity to r.
But after R also we are moving further more to dr minus t. So
I am bringing it from infinity to r, and dr is just a small displacement happening at that.
that's negligible.
Negative, positive, we are already done about that.
Yes, sir.
We are only trying to understand why am I integrating.
And yes, sir. That is
To know what is the work that is done from infinity to r, how much it is done.
Yes, sir.
Only if I take this much Fe into dr, that is the minute energy that I had to use. That small.
Yes, sir.
But from infinity to this particular point P will tell me the total energy that I have given.
Yes, sir.
Is this clear?
Yes, sir.
Now, so basically I will get this as electrostatic force is basically K small q capital Q by R square into dr, and the limits are from infinity to R.
Yes, sir. They're constant. So
Integral of dr by R square is what?
will be minus 1 by
Minus 1 by R. And from infinity to R, so basically I'll get minus K capital Q small q into, I brought the minus sign out of it, upper limit minus lower limit, correct?
Yes, sir.
This is minus K capital Q small q divided by R. Is this clear?
Yes, sir.
See, what is this? This is the work done by the applied force.
Yes, sir.
Are you getting my point?
Yes, sir.
There is a concept now I want to discuss with you. There is a concept that I want to discuss with you at this particular. So we are done with the mathematics.
Yes, sir.
Now we have to understand it further. Then I will give you a brief of from the start to the end.
Yes, sir.
Same marker example. Let us say from here to here, I have used 10 joules to raise this marker.
Yes, sir.
But while I am raising this marker and using my 10 joules, first thing is, how am I using this 10 joules? By applying force Fa.
Yes, sir.
But while that is happening, Fg is also acting on it, which is the gravitational force.
Yes, sir.
So just now I told you that I used 10 joules. Now I'll leave it. The same 10 joules it will utilize.
But some of it is being lost.
While going down, it is lost.
Yes, sir.
Not some of it, everything is lost.
Yes, sir.
That is for sure. From here, I used 10 joules to bring it here and again leave it. It will go back. Same 10 joules is utilized.
Yes, sir.
But I have a doubt. When I am lifting it, my 10 joules, leaving it, the marker is using the same 10 joules, correct?
Yes, sir.
There is gravity in all of it. Is gravity sleeping through this entire story? Gravity should also have something to do with it, right?
Yes, sir.
Are you getting my point?
Yes, sir.
We'll go slow about it. I am not in a hurry because this is a concept which can be manipulated and easily manipulated by yourself also in future. Not by yourself. All the students of country of India, 100% sure.
Yes, sir.
No doubt. See, understand this. Marker is here. Earth is there. I am here. My left hand is here. Use 10 joules to lift it. Great. Even a first class fellow will understand. Leave it. The same 10 joules is used back to go down. Great.
Yes, sir.
I gave 10 joules and it used those 10 joules. Great.
Yes, sir.
But from beginning to end, I am not talking anything about gravity. Gravity is also there, right? Simultaneously.
Yes, sir.
Here is the story. As I am using 10 joules to lift it from here to here, the work done by me is 10 joules.
Yes, sir.
The work done by gravity will be minus 10 joules. I'll prove it in this particular situation.
Sir, then
I'll prove
the
it.
force you are taking,
Can I
the
prove it?
marker upward will be zero.
Can I prove it?
Yes, sir.
I just told you in this simple example, but I also have to write mathematics. Actually, we explain this in work energy using the same example. I also draw that particular thing over here, but we are in electrostatics. We can use electrostatics, no problem. And then we'll see how these examples will match.
Yes, sir.
Let me do the mathematics. So just now we said, but I'll go back to the definition part. Work done by the applied force is applied force dot dr bar, correct? Or minus dr, whichever.
Yes.
Similarly, work done by electrostatic force can also be written Fe bar dot minus dr bar.
Yes, sir.
Yes or no?
Yes, sir.
Fa and Fe are anti-parallel to each other.
Yes, sir.
That is for sure.
Yes,
Fa
sir.
bar and Fe bar are anti-parallel to each other. Is this clear?
Yes, sir.
But
Yes,
the
sir.
magnitudes are same. Fa is equal to Fe.
Yes, sir.
Displacement anyways is same.
Hmm.
In this dot product, if I have cos 0, in this dot product, I will have cos 180.
Yes, sir.
The only difference between these two I will have is cos 0 and cos 180.
Yes, sir.
Cos 0 is 1, cos 180 is minus 1.
-1.
Suppose if I will get this as 50 joules, 100 joules, but I am just using an alphabet. Suppose I'll get this as, we will use Q1, okay, because Q already we used it for charge. Okay, I'm just
Yes,
using
sir.
some alphabet. Q1 joules of energy we got here. That means here
Yes.
I should get minus Q1 joules, obviously. Magnitudes are
Yes,
same.
sir.
Only cos 0 and cos 180 difference. So here if I get 100, I should get minus 100.
Yes, sir.
Here if I get 50, I should get minus 50.
Yes, sir.
Same example over here. If I am lifting this marker using my left hand very slowly, I don't want to play with kinetic energy. I'm already suffering with potential energy. I bring kinetic energy.
Yes, sir.
Lift this marker from my hand to above, I have to apply equal magnitude of force as that of the gravitational to maintain kinetic energy constant.
Yes, sir.
First, I have to apply equal amount of force as that of gravitational force in this example.
Yes, sir.
If the magnitudes are same and anyways displacement is same.
So then if force applied by the gravitation and force applied by by your hand are same and they're in opposite directions, they cancel. So how is the energy getting stored?
Good, that this is the problem, not with you, everybody in the country. I was going to wait, relax. I'm not that fast. Slowly, hole hole. So you're saying the gravitational force is in the downward direction, my applied force is in the upward direction. Forces are cancelling each other.
Yes, sir.
Yes, you are right. Forces are cancelling each other.
Where is energy getting stored?
How is energy getting stored?
Yes, sir.
Where we don't know, but how is energy getting stored?
Yes, sir.
Every force will have its own energy when we specifically talk of potential energy. I'll give you a small example. So let me say I am fighting Mike Tyson. And Mike Tyson wants to punch me. But I am a physics faculty. So I will use my brain. I will say force applied is equal to force replied. Newton's third law, action force, reaction force. No problem. You apply force on me. My chin will apply force on you. They will cancel each other. So no problem. Hit me. There should be no end result, right? They should cancel each other.
No, sir.
The applied force will do its job. The replied force will do its job. But the end result is gone. What
Yes.
I am trying to say is that your doubt is a very common thing, and okay, applied force and gravitational force are opposite to each other, therefore they are cancelling each other. Correct, I agree. So what? Now you are saying how is the energy stored? How energy is stored, we have to ask scientists. How literally? Okay. But we have already figured out that wherever there is force, there is a representative potential energy associated.
Yes,
Wherever
sir.
there is force, there is a representative work done. Therefore, there is a representative potential energy, respective potential energy. So, for my applied force, I will have applied potential energy. For my electrostatic force, I will have my electrostatic potential energy. For my gravitational force, I will have my gravitational potential energy. All these three will be playing around simultaneously.
Yes, sir.
Everything will be there. Where do you have Arabic force? You will have Arabic potential energy. Why not? I'm not joking. Because there is gravitational force, we have something called gravitational potential energy. Because we have electrostatic force, we have something called electrostatic potential energy. Now bring Arabic force, you will have Arabic potential energy. Naxal force, Naxal potential energy. Wherever there is force, there is potential energy. That's the concept that we discussed, right? Language that we discussed. Get concept.
Yes, sir.
The language part of it that we discussed is wherever there is force, there is a potential energy associated with it. Now, what type of force it is, your wish, you can create. Somebody called it gravitation, somebody called it electrostatic force, and one is magnetic force. I want to say boom boom force, boom boom potential energy. Wherever there is force, there is associated potential energy. Therefore, you call
Yes, sir.
anything. Here I have applied force. So that applied force will also have its own applied potential energy.
Yes, sir.
Gravitation is also acting simultaneously when I am pulling it upwards.
Yes, sir.
If gravitation is not acting, then force, where am I applying? Why am I applying? Leave it there. Remove hand and run away. The marker should be there only. Because gravitation is acting downward, because electrostatic force is acting right side, I am applying a force left side, and that I am doing to keep my kinetic energy constant,
Yes, sir.
so that I don't have to meddle with kinetic energy. And while doing this entire thing, because now I have two forces, applied force and electrostatic force, therefore I will have electrostatic potential energy, I will have applied potential energy also simultaneously.
Yes, sir.
But that applied potential energy is being delivered to the system, and that electrostatic potential energy is being taken by the system.
There will gravity also play a role here?
In this, we don't have gravity right now. In this, we have gravity.
Yes, sir.
But the story is the same. Here, gravitational force, here, electrostatic force. How does it matter?
Yes, sir.
The applied force will have applied potential energy, correct?
Yes, sir.
Now we are trying to understand the form in which way it is being utilized in this situation. The applied potential energy is being granted, given to the system. And that
Yes, sir.
particular energy is being taken by the system as electrostatic potential energy.
Yes, sir.
Both are occurring simultaneously.
Yes, sir.
Are you getting my point?
The force, everything you are applying is being stored in the charge.
Energy is being stored in the system. Force is not
Yes, sir.
stored in the charge.
Yes, sir.
Too much English. The energy that I am using to bring the charge from here to here is the same energy that is being stored. Okay?
Yes, sir.
But the English that we use, the problem. What is that
Yes.
English that I am talking of? The applied work done will have its own respective applied potential energy also, which I will write it as minus k capital Q small q by r. I am giving this CBA, that's why I am writing it as negative. Getting my point?
Negative represents that it is bonded to the system.
And it is a change in potential energy. Yeah, tell me what?
Negative represents it is bonded to the system.
I don't know that much of physics. Slowly, slowly, okay. What negative represents, I am not focusing on that. I am focusing on there is something called change in applied force potential energy also.
Yes, sir.
First, I am focusing on that. See, both the situations are happening simultaneously, and here, because you have seen whatever this value is there, here I have a negative value of that, correct?
Yes, sir.
That means my work done by this applied force, if it is this, the electrostatic force should be this.
Yes, sir.
Which should give me the change in potential energy of the electrostatic force.
It should be positive.
That means what I am trying to say from here is the electrostatic potential energy of the system when the charges are at a distance of r is equal to k capital Q small q by r. Is this clear?
Yes, sir.
Understood.
Yes, sir.
See, what we are trying to understand over here, I will repeat the ending story again in terms of numbers. I used 10 joules to bring this charge from here to here.
Yes,
I
sir.
gave it 10 joules. The change in energy of me should be minus 10 joules.
Because you are giving it, it's lost from you.
It lost from me. Here I am talking of change in applied potential energy. Minus 10 joules. Correct?
Yes, sir.
Now the same 10 joule energy is transferring into the system as electrostatic potential energy, the magnitude will be the same, but now it will be positive. The change in electrostatic potential energy will be plus 10 joules.
It's like we have conventions in thermodynamics.
That's exact. They're also work done energy only, right? Actually, if you look at it, there also work done word is there. You have change in energy word is there. Therefore, you have the same conventions everywhere. I had 5 chocolates. I gave it 5 chocolates. Now that fellow has 5 chocolates.
Yes, sir.
What is the change in chocolates in me? Minus 5. What is the change in chocolates in it? Plus 5. All this minus 5 plus 5, whatever it is, eventually that 5 chocolates are running from one place to other.
Yes, sir.
Like you said, you use whatever convention that you want to use to confuse all the students all over the country. But eventually the story is about the 5 chocolates which are going from one pocket to other pocket. That's it.
Yes, sir.
Is it clear?
Yes, sir.
Let me rinse and repeat. Here I could write this work done directly in terms of change in potential energy because I kept the change in kinetic energy 0, by the way. Okay, and the reason to keep change in kinetic energy 0 was to eventually find out what is the potential energy of electrostatic potential energy of 2-point charge system. Okay, but there was a lot of concepts of mechanics over here.
Yes, sir.
So I'll start off right from the beginning. I have one fixed charge plus capital Q, and I have one movable free to move charge plus small q. They both are at infinite distance initially. Because there is infinite distance, the electrostatic force of interaction between them is 0. There is no topic of any kind of a potential energy story. Why? Because we spoke about the language part of it. Wherever we have some kind of a force, we can talk of some kind of a potential. Or wherever we talk about potential, it has something to do with some kind of a force or a strength in it, right?
Yes, sir.
So, initially, because the force of interaction is 0, therefore there is no story to talk about potential energy of any of the system. Now, I want to bring this charge from infinity to a particular distance r. But I want to bring it very slowly, keeping the kinetic energy constant. Kinetic energy constant means the change in kinetic energy through the journey is 0. I have to have some kind of kinetic energy because otherwise motion is not described. But what I am trying to maintain is the change in kinetic energy I am maintaining 0. Clear?
Yes, sir.
To maintain change in kinetic energy 0, that means to maintain constant velocity because mass is constant, right? If I have kinetic energy, change in kinetic energy should be 0, that means change in velocity should be 0. To maintain change in velocity to be 0, I have to maintain change in momentum to be 0. To maintain change in momentum to be 0, I have to have the net force to be 0. And to keep the net force to be 0, I have to maintain the applied force equal to the electrostatic force in opposite direction. At every point in the journey, through the journey, I have to do this. Just to maintain change in kinetic energy to be 0.
Yes, sir.
Now I have at least come to the situation where my applied force is always equal to the electrostatic force. Clear?
Yes, sir.
Then we came to this situation where we said wherever there is force and of course displacements involved, I can talk about work done, which is vector dot product of force and displacement. Yeah? Any doubt?
No, sir.
Which is vector dot product of force and displacement. Because I am bringing this charge from infinity, that is right to left, I am further moving it in the same direction, minus dr.
Yes, sir.
Why is this minus? because the other fellow I wrote it as plus. That's all.
Yes, sir.
Anyways, irrespective of minus plus stories, we saw that the force vector, applied force vector, and the displacement vector, while bringing it towards, are both parallel.
Yes, sir.
Therefore, the work done by the applied force is going to be the dot product of FA and minus dr bar.
Yes, sir.
And because they are parallel, angle between them is 0. So mod A, mod B cos 0. Therefore, I can just write it as AB.
Yes, sir.
The magnitudes are the same, FA and FE. Therefore, I am substituting this. Clear?
Yes, sir.
Then, if I am writing, actually this is also WA. If I am writing FE into dr, I am bringing the charge system from infinity to whatever point B. So I need to integrate, right? Because it's a varying force all the time.
Yes, sir.
Because Fe is a variable all the time, I am integrating limits from infinity to R. What is
Yes.
Fe? Kq by R square. Kq by R square. dr. Integral is minus 1 by R from infinity to R. I got it as minus Kq by R. But what is this minus Kq by R? This is the work done by the applied force.
Yes, sir.
I am giving 10 joules of energy. Are you getting my point?
Yes, sir.
Understood. Now I am
Yes.
telling you that work done by applied force is applied force dot product with displacement vector. Work done by electrostatic force is electrostatic force dot product with displacement vector. Applied force and electrostatic force are anti-parallel with each other. Obviously, if this dot product has cos 0 in it, this dot product will have cos 180 in it.
Yes, sir.
Say that if this fellow's value is plus q1, this fellow's value will be minus q.
Yes,
So
sir.
if I am using 10 joules of energy to lift this marker from here to here, simultaneously gravitation is using minus 10 joules of energy to lift the marker from here to here. The common
Yes.
factor in this entire story is lift the marker from this position to this. The common point over here, the common factor over here is bringing the charge from infinity to R bar.
Yes, sir.
Both the forces are applying, applied forces also applying, electrostatic forces also applying. Both are simultaneously being applied on the object. That's how my change in kinetic energy is 0. But whenever there is a force, there is an associated potential energy. That means my applied change in potential energy will be minus kqqq by R.
Yes, sir.
And the electrostatic change in potential energy will be plus kq R.
Yes, sir.
Or in simple terms, to bring the charge from infinity to here, it will not come automatically. I will have to bring it. So I am giving it 10 joules and it is receiving the 10 joules. Simple.
Yes, sir.
And that 10 joules of energy is stored as electrostatic potential energy.
Yes, sir.
Exactly, if I have to say that 10 joules is being stored as increase in potential, electrostatic potential energy.
Yes, sir.
That 10 joules is lost in me as decrease in applied potential energy.
Yes, sir.
Is this clear?
Yes, sir.
Ultimately, we are coming to a point which we wanted to end up. That is, what is the electrostatic potential energy between 2-point charge system plus q and small q placed at a distance of r? It is plus kqqq by r. Is this clear?
Yes, sir.
Rocks. Hi guys, I hope you enjoyed the session. If you think this video was useful, don't forget to like, share and subscribe to my channel. Also, I'll be waiting for your comments in the comment section. See you in the next video.